So we're going to look at each of these carbons and see how many different things it's bonded to. So this would be carbon number 1, number 2, number 3, and number 4. So I'm reading from right to left because the OH group is nearer to the right hand side. So carbon number 1, we've got 3 hydrogens and it's bonded to 1 carbon for the group. So it's only got 2 different groups, so that's not going to be a chiral carbon. Moving along to carbon number 2. This one is bonded to a carbon of a CH3, so that's 1 group. A hydrogen, that's different, so that's a 2nd group. An OH, that's a 3rd group. And a C2H5, yet another group. So this is a chiral carbon. So we've identified a chiral centre within the molecule. So if we move along, so this carbon, it's got 2 hydrogens, 2 of the same thing, so it can't have 4 different things. So that's going to be a little shortcut for this. So this isn't chiral, and down the end it's the same picture as the other CH3. It's got 3 of the same thing. It's not a chiral centre. So this molecule is chiral, and I've identified the chiral carbon is to be carbon number 2. So this one does display isomerism. Now, if we take an isomer of butan-2-ol, so if we take butan-1-ol, and consider this one. So this carbon here, it's just bonded to 3 hydrogens, so it's not chiral. It hasn't got 4 different things. This one, 2 hydrogens, okay, not chiral. CH2. 2 hydrogens, 2 of the same thing, can't have 4 different groups, not chiral. And then we get to the end here, so this C bonded to 2 hydrogens, so it's got an OH, a C, but 2 H's, and so this is an achiral molecule. An achiral or non-chiral molecule. Achiral is the more common terminology for it. So I'm going to set you some questions where I want you to go and try and identify the chiral centres in the molecules. It is entirely possible to have more than 1 chiral carbon. You're not going to see that in exam questions, but it very much does exist. And I believe the questions I'm going to give you, they've got some multiple chiral carbons, just to make it a little bit more challenging because it's using the same skill. And if we look back up to the thalidomide, we'll see if we can identify where the chiral carbon is in this molecule. It will be in the same place for the R and the S version. They're just mirror images of each other. So we'll just look at the S thalidomide. So we've got, let's start working left to right. So we've got all the carbons in the benzene ring. These only have 3 bonds. It needs to have 4 bonds in order to be chiral. So because it's got the sort of, it doesn't actually have these double bonds. It's a bit more complicated. We'll do that in a future topic. It only has 3 bonds. It's got a bond to the carbon, a bond to another carbon, and then a bond out to a hydrogen that's not shown, usually because it's skeletal representation. So it can't have 4 different things because it's only got 3 bonds. Over here, so this carbon, double bond to the oxygen, single bond to the carbon, single bond to the nitrogen. It's only got 3 things, so it can't be chiral, and same with the one down here. Nitrogen doesn't display chirality. Then we get to this carbon here. So this carbon has got a nitrogen, a hydrogen, and then 2 carbons. Now, this carbon, this is a carbon then bonded to a nitrogen, this is a carbon then bonded to a carbon, so they're different to each other. They're part of the same group, which is why this can be confusing, but we've got to look, going around this way, is that identical step by step as you go round to going round this way, so going clockwise and anti-clockwise. And they're identical to start with, but then you move one along and they're different from each other. So they can be considered different groups. And so this carbon here, labelled with a star, that's the chiral carbon because it has 4 different things. And that's what differs. This is where it's sort of mirror imaged around between the 2 molecules. Okay, so we're now going to look at the last thing, which is representing the enantiomers. So showing them in diagrammatical form on a 2D piece of paper, which presents problems because this is very much a 3D thing we're working with. So we'll use this molymod from earlier as the molecule we're going to draw. So just quickly some notation. You've probably seen these before. We had it in that diagram of the thalidomide before. Is our wedges and our hashed lines. Now I think we went over this in class last year very briefly, but it didn't matter too much. This means coming towards you. This is coming out the plane of the paper. So if I try and lay this down flat against the paper, this green one, for example, is coming towards you, and so we would use a wedge like this to show it coming towards you. It's trying to use perspective. Now the lines, this is going away. So this is going away. So in this reddy orange one is going away from you back into the paper, and so this one will be represented with a wedged line. Now all the chiral molecules you're going to have to draw, you've got a carbon bonded to 4 different things, and you just want to follow a pattern, because the number of very, very weird representations that get shown is pretty remarkable, and it's difficult to do it. This requires a lot of 3-dimensional thinking, which for a lot of people is just very, very, very difficult. I think it's often find it's a thing you either have or don't have, and it's very, very difficult to learn. So we're just going to have sort of a pattern that you can follow. So we've got our tetrahedral shape around our carbon. We're going to start by drawing a line up, and we're going to draw a line going over to the left. We then have one coming towards, and then one going away. And you see how this is trying to show the same shape as I'm holding here. So we've got this one here, that's sort of flat to the plane of the paper, the one going up, the one going towards, and the one going away. So I'll label, so I'm then going to match the groups onto this shape here. So this one, the purple one, I'll put a P. We'll say this one is red, put an R. Green, and then W for white. So that is representing our first molecule. We're then going to mirror image it. So just basically use the skills you learned in primary school or Key Stage 3 maths to sort of do the mirror image of that. So draw the carbon, don't actually mirror image the letters, just the shape. One line up, the flat line goes away. We've got a wedge on the left and a dashed line on the left as well, and then map over the letters, so all the different groups. So the G, the green, goes down there, the red there, the purple up the top, and the white there. And so this then lines up with the moly one I prepared earlier. Oh, no, it doesn't. There we go. And so these are then the mirror images of each other. Okay, so the very last thing we need to go over is how the 2 different enantiomers might be distinguished from each other. So how we might identify if we have a sample of one enantiomer or the other one. Because chemically they're essentially identical to each other. There's no chemical test for it. There might be some fancy enzyme tests for some molecules, but really there's very, very, very difficult to tell. So the way we identify it is using something called plane polarized light. So it's really something from physics. It's not something I'm an expert in about how to explain what plane polarized light is. But you certainly would have learned at GCSE that light is a wave, it's oscillating. But most of the light we normally come into, it's oscillating in all sorts of different directions. So the oscillation is not just up and down, it could be side to side, diagonally. I think it can even be like a spiral shape, the oscillation. But plane polarized light, they use something called Polaroid filter. You might want to go and read up on what a Polaroid filter is, they're quite interesting. They're used in the Polaroid sunglasses, that's where that brand name comes from. And what it means is the oscillations only are in one single plane. There's no different ways they're oscillating, they're all oscillating the same way. So all the rays of light have the same plane of oscillation. And so let's say the plane they oscillate on is sort of flat and it's going like away from us, and so it's oscillating along 0 degrees. Now we're going to take that plane polarized light, we're going to pass it through a sample of our molecule. Now one of these, this will either be, one of them will be the plus enantiomer, and one of them will be the minus enantiomer. Now I have no idea which one it is. I believe it is borderline impossible to predict which one it's going to be, which one's going to be plus or minus. It just has to be found experimentally. Now if we pass the plane polarized light through the positive enantiomer, it's going to rotate the plane of polarization round this way. So the light might pass through the sample of this, the plane of polarization will get rotated, and so when it comes out the other side, maybe it'll be at 20 degrees like this. So the plane of polarization gets rotated. If we pass the sample, pass the plane polarized light through the negative, instead it will rotate it the other way, and so the plane of polarization will come out